2.6 Lie groups. Groups that are also manifolds. Before we can describe Yang-Mills fields and gauge covariant derivatives, we must learn the math language of Lie groups. 2.6.1 Introduction. A Lie group is a group that is also a manifold, in which the operation of group multiplication is a diffeomorphism. Left multiplication. L sub gh equals g of h of open paren g. H is a member of G close paren. Then L sub G colon G goes to G is a diffeomorphism.
Right multiplication, R sub GH equals H of G is also a diffeomorphism. The adjoint map A sub G is defined by A sub GH equals G inverse of H of G, which is also a diffeomorphism. See equation 2-70. Given a vector xi to the A at the identity E of G, the diffeomorphism L sub G produces a vector L sub G star xi to the A at L sub G of E equals G of E equals G. In other words, there is a vector field on G.
See equation 2-71, which is obtained from xi to the A of E by left multiplication. So, see equation 2-72. Thus, to each tangent vector in T sub E-G corresponds a left invariant vector field on G, i.e. left invariant L sub G star times open paren, xi to the A close paren subfield, equals open paren, xi to the A close paren subfield. It can be proven that the Lie bracket open bracket xi vector, eta vector close bracket of two left invariant vector fields xi vector, eta vector is itself a left invariant vector field. Also, if psi sub lambda is the family diffeomorphisms generated by xi vector and phi is another diffeo, then phi psi sub lambda phi inverse is the diffeo generated by phi sub star xi vector.
See equation 2-73. And see equation 2-74. At phi of x, phi sub star of xi vector of x is tangent to the path lambda goes to phi composition psi sub lambda of x. So, phi sub star of xi vector of phi inverse of x is tangent to lambda goes to phi composition psi sub lambda composition phi inverse of x at x. Thus, phi sub star xi is tangent at x to lambda goes to phi composition psi sub lambda composition phi inverse of x. Therefore, phi sub star xi vector generates the diffeomorphism phi composition psi sub lambda composition phi inverse. Now let phi equals L sub G.
See equation 2-75. Thus, see equation 2-76. Since xi vector and eta vector are left inv phi sub star xi vector equals xi vector, phi sub star eta vector equals eta vector, four fields. So, see equation 2-77. And the bracket is proven to be left invariant as well. The vector space T sub E-G can be identified with the vector space of left inv vector fields on G. T sub E-G is closed under the Lie bracket, justifying the name Lie algebra.
If xi to the A of E and the A power of eta of E are vectors at E times epsilon times G, then open bracket xi, eta close bracket to the A times E is a vector at E. Since open bracket xi, eta close bracket is linear in xi and eta it defines a bilinear map T sub E-G times T sub E-G goes to T sub E-G. Thus there is an antisymmetric tensor C sub BC to the A on BC at E with. See equation 2-78.
Define C sub BC to G to the A equals L sub G star C sub BC to E to the A, then C sub BC to the A is left invariant. And see equation 2-79. C sub BC to the A is known as the structure tensor of the Lie algebra, and the concrete values C sub ij to the k are the structure constants of T sub E-G.
Example 2.6. A. Prove that W to the A equals open bracket U, V close bracket to the A is a vector field by proving that the Leibniz rule is satisfied. B. Show that in any chart, open bracket U, V close bracket to the K equals open paren U to the I partial differential sub I V to the K minus V to the I partial differential sub I U to the K close paren.
Solution. Let's start with, see the equations shown. Thus, see the equation, and the Leibniz rule is satisfied. B. In a chart x colon V of f equals V to the I partial differential sub IF. Thus, open bracket U, V close bracket times f equals U of V of f minus V of U of f goes to open bracket U. v close bracket to the k partial differential sub kf equals u to the I partial differential sub I open paren v to the j partial differential sub jf close paren minus v to the j partial differential sub j open paren u to the I partial differential sub if close paren.
So, see the equations shown. Thus, see the next equation.
Example 2.7. A vector lies in a submanifold M of n if it is the tangent to the curve C of lambda that lies in M. Prove that a vector v to the a at a point P is a member of M lies in M if and only if v to the gradient sub af equals 0, for all functions f on n that are constant on M.
B. Show that if u to the a and v to the are vector fields on n for which u to the of P and v to the of P lie in M when P is a member of M, then open bracket u, v close bracket to the a similarly lies in M. Show that open bracket u, v close bracket to the a gradient sub af equals 0, f constant on M.
Solution. In a given chart x to the I we have v to the gradient sub af equals v to the I partial differential sub if. If the dimension of M is M and N is N, then we can arrange I equals 1.M.N such that the first M coordinates are a basis for the submanifold. Now, see the equation shown. Now, if we specify all functions which are constant on M under F, then all the derivatives partial differential sub if, partial differential sub MF are 0, so, see the equation.
If for all f this vanishes, then each of the v raised to the m plus 1 power, v to the n must be 0. Thus if v to the gradient sub af equals 0 for all f on n that are constant on M, then v to the I can only have non-zero components I equals L.M, i.e., v to the a lies in M. The converse. If v to the a lies in M, then the I equals m plus 1 and components must be 0, and if the function f is constant on M, i.e. partial differential sub if equals 0 for all is a member of L.M. The v to the I partial differential sub if equals 0 gives v to the gradient sub af equals 0.
B. We have v to the I partial differential sub if equals 0, and u to the I partial differential sub if equals 0 for the f as specified. See the next equation. Let I sub m equals L.M. I sub n equals m plus 1 n. Then, see the equation shown.
2.6.2 The general linear group bold italic G bold italic L sub bold italic N times bold italic R. The Lie group might be very general, such as in G of L sub N of R. The general linear group G of L sub N of R is the group of inventable N times N matrices A equals norm A sub J to the L. Any other group of matrices is a subgroup of some G of L sub N. Natural coordinates on G equals G of L sub N, and the n-squared matrix elements A sub J to A to the I is a member of G. The associated coordinate basis, partial differential A sub J to the I consists of vectors tangent to curves.
See equation 2-80. If V is tangent at E to the path G sub J to lambda to the I, its components along the natural coordinate basis are. See equation 2-81, where. See equation 2-82. Thus, a left invariant vector field V on G has components V sub J to A to the I at A is a member of G obtained from its components at the origin by left multiplication of V sub J to the I by A sub J to the I.
Now consider the parameter subgroup defined by. See equation 2-83. Where V is the matrix norm V sub N to the M. Then, see equation 2-84. Is the L parameter family of diffeomorphisms generated by the left INV vector field V vector. See equation 2-85. Thus, the left INV vector fields V vector generate right multiplication by E raised to the lambda x power. For another interesting property, consider UV. See equation 2-86.
Where? See equation 2-87. Since. See equation 2-88. We have. See equation 2-89, which is a simple relation between the Lie bracket, UV, and the commutator of two matrices.
Example 2.8. In the group G of L sub N, find the left invariant vector field Z sub J to the I that agree with the vector the fraction with numerator partial differential and denominator partial differential A sub J to the I at the identity. Compute the structure constants C sub j km raised to the I script ln power defined by open bracket E sub k to the script L power, E sub m to the n close bracket equals C sub j km raised to the I script ln power E sub I to the j. Partial solution.
Start with the fraction with numerator partial differential and denominator partial differential. A sub j to the I is tangent to a sub j to lambda to the I equals norm a sub n to the m plus lambda delta sub I to the m delta sub n to the j. Rename E sub j to the I by V sub j to the I for notational convenience. So have that V sub j to the I is left unvariant if V sub j to g to the I equals open bracket L sub g raised to the star power V of E close bracket sub j to the I. For g of L sub n, left multiplication corresponds to matrix multiplication. Let V sub j to e to the I equals the fraction with numerator partial differential and denominator partial differential a sub j to the I, i.e. V sub j to e to the I is tangent to a sub j to lambda to the I at lambda equals 0. The left invariant vector fields V sub j to the I that agree with the fraction with numerator partial differential and denominator partial differential a sub j to the I at the identity are.
See the equation. Now consider open bracket V sub k to the script L power, V sub m to the n close bracket equals C sub j km raised to the I script ln power V sub I to the j to proceed. The rest is left to the reader.
Example 2.9. Prove the Jacobi identity by A. Showing for any three vector fields u, v, w that. See the next equation. B. Showing that for any Lie group, the structure constant tensor satisfies. C sub d open bracket a to the e c sub b c close bracket to the d equals 0.
Solution. We consider a local coordinate system, then. See the equations shown. Using the Jacobi identity and the definition of the structure tensor. See the equation shown. With open bracket x to the a, y to the a close bracket to the c equals c sub a b to the c x to the a y to the b we have. See the equation.
See the next equation. If we add up cyclic permutations we get. See the equations shown. For general u, v, w we then get open paren c sub ad to the ec sub bc to the d plus c sub bd to the ec sub ca to the d plus c sub cd to the ec sub ab to the d close paren equals 0. Consider the lower three free indices and ask if we have antisymmetric on a left goes to be yes. Same for A and C and B and C thus fully antisymmetric, thus have. See the equation shown.